Alright, so we're going to learn about the inverse function today. So an inverse function is a function that can undo or reverse an original function elsewhere. To know if something or an inverse function exists on an original function, then there's a test you can do on it. It's called the vertical line and the horizontal line test. So suppose we have a parabola or parabola, if you want to say it properly, then you can do the vertical line test, and you know that it passes because there's only one point of intersection at any given time, so you know it's a function. But if you do the horizontal line test, what you discover is that there are parts on the graph that are going to cut twice. And because of that, it fails the horizontal line test, and there's no inverse function. The reason for this is you have multiple outputs for any singular input. And if you've got multiple outputs for any singular input, you can't really reverse that because it's got to have one output for every single input, basically. Does that make sense? Now suppose we have a look at a different function, a hyperbola. These are interesting creatures. Sure enough, if we do a vertical line test on this, no worries. I mean, there's going to be a few, or there's going to be one value that doesn't exist, but that's fine for the input. But for the output, for every value that you put into it, there's going to be a unique output. And because of that, it passes the horizontal line test. Such a function that passes both the horizontal and the vertical line tests, we call it a one-to-one function. On the other hand, if it fails the horizontal line test, we call it a one-to-many or a many-to-one. I can't remember which one it is. But it's still a function. It's just you can't get an inverse for it because it doesn't match up one-to-one. So key language here, a function with an inverse is called a one-to-one. Oops. Now the question is, how do you find an inverse function? And there's two ways you can do it. One, you can do it graphically, and the other way you can do it analytically or algebraically. First one we're going to look at is how to do it graphically, and then after we've done the graphical method, I'll show you how to do the analytical method. There's merits to both of them here. And we'll keep it nice and simple. Oops. F is the machinery that transforms x into 2x plus 1. And the first way we're going to do it is graphically. So, if we have to do something graphically, what do you reckon we have to draw? A graph. So, here's a graph. Not too big, but it will do for now. It's my x, this is my y-axis. positive direction. Now, when you're doing this, if you're doing the graphical method, you have to do it accurately. I'm just going to sketch for now because I got no choice on the board. I know that it's going to cut the y-axis at 1, and it's going to have a slope of 2. Like that. Now, to do this graphically, what we find is that if there's an inverse function to this and it's 1 to 1, then by definition, do it in orange, this line over here is y equals x. If it's a 1-to-1 function, what you discover is that the inverse function is reflected about the y equals x. So all you need to do is you find 2 points and then you sketch in the next one. So I will do it in black. This point over here, do we know what it is? Yeah, what is it?
0, 1.
0, 1. Now, if this is going to be symmetrical about the orange line here, y equals x, what we're going to find is that the symmetrical one's going to cut at 1, 0. And if it's symmetrical, they're going to cut here as well. So what you can do is you can just line up your ruler. Not bad, right? And there's your function there. That's the inverse. But we don't have an equation for that, do we? So here goes to the next level of complexity. Partially analytically, using slope-intercept.
Is the top one, is that the 2x plus 1 the function?
Yeah, 2x plus 1.
So like the top purple line? Yeah.
This is y equals f of x. And this one over here is y equals inverse f of x. Does that clear up the ambiguity?
Yeah.
Yeah, sorry, I should have written that to begin with. Okay, next way we can do this is partially analytically, slope-intercept. Now think about it. If this is the inverse of this, then the gradient of the inverse function is going to be 1 over, and what is the gradient of this top one? 2. So 1 over 2, so it's a half. Secondly, do we have a known point for our inverse?
Yeah.
What is it?
1, 0.
1, 0. That's x1, that's y1. So all you need to do is put it into the slope-intercept form, or you can do general form, it doesn't matter. I'm not going to do general because I rarely use it, if ever. But you go y equals, or y1 equals, mx1 plus c. y1 is 0, x1 is 1, the gradient is a half plus a c, so your c is going to be negative a half. Hence, which is the same as saying is that cool? Sorry, it's a little bit messy there. I just compact it. So that's partially analytically. You're relying on the graph to be able to deduce the function. Is that cool? And here's the final one. This is my favorite way to do it because it requires the least amount of effort.
These all different ways?
3 different ways. You have to know each different way because in the SATs and the externals, it is very common for us to give you what's called an understanding question. So we might give you something that doesn't have an equation on it, and we might say sketch the inverse using the graph. Here's an accurate graph of a function, find the inverse. So you might have to sketch it, and then from sketching it, you might have to extrapolate the information. Does that make sense? Or we might say, here's 2 functions, determine if they're the inverse of one another. And you have to just work with it on the Cartesian plane. Does that make sense? The reason why we'll give you a question like that as well, in the real world, it is really rare. Like in practice, it's really rare that you'd get given that. You sort of just get an output on a screen for empirical data, and then you just have to work with it through correlation if you wanted, or just higher. Okay, so final one. This is my favorite way to do it. This is analytically. Yeah, analytically. That's a good way to spell it. Okay, so first one we have given our function is machinery that turns x into 2x plus 1. What you can do is you can write this as y equals 2x plus 1. Do you agree? Next step, what we're going to do is we're going to go for the inverse here. Wherever I see y, I change it to an x, and wherever I see x, I change it to a y. Freaky, right?
Yeah, that's actually kind of weird.
Then we simply arrange for y. So it's going to be 2y, x, take 1, y equals x, take 1, not over y, over x.
Over X? Over 2.
Oh, sorry, over 2. Just checking. So we swap. Swap the variables. Hence,
I'm not actually. Yeah.
I would feel bad at least. Yesterday. Feel bad at least.
so therefore, analytically, you can easily find the inverse function as well. Does that sound cool?
Yeah, I think I like the better.
Yeah. All right. Are you happy with that, or do you want to discuss one more concept as well?
Maybe go on to question.
So for the inverse orange line, is it always y equals x?
Yeah, it's always, because it's always symmetry about this line here. Yeah. So you can be like, oh, well, if this line looks like that, it cuts here, so it'll cut there, and therefore they both have to cut at a common point. So.
What question do you want?
We are looking at question 1 AB, question 2B, question 3 ABC, question 4, question 5, question 6 AB, question 7, question 9, question 10, question 11, then question 13, question 14, question 16, all followed down or washed it down with question 17, A, B, and E.
So just literally every single question but maybe a couple.
Well, you're missing some.
My man.
You're going to do them all.
Are we able to do